All right. Hello, everybody. My name is Swati, and I'm an application engineer here in MapleSoft, and I will be the presenter for today's workshop. All right. So today's workshop, like I've mentioned, is modeling and simulation of hydraulic systems in MapleSim. Before we dive into the example models, I kind of want to show you the different library components that we have for the hydraulics library. So just going over the components here. All right, so we have pipes, different types of pipes that you can include in your model, restrictions, orifices, table-based as well as normal. We will get to a detailed explanation about some of these components when we do the examples. We have actuators, we have sources, we have different types of motors and pumps, table-based pumps that allows you to put in the pressure versus the head characteristic curve inside, different types of accumulators, spring-loaded and gas-loaded accumulator, different chambers that adds compliance to the model, sensors to sense the pressure, flow rate, measurements. We have different valves that you can add to the model as you build your system. And we also have a table-based valve, which I'll get to pretty soon, but this table-based valve allows you to put in characteristic data. And of course, under direction control valves, we have three different sections: 3-way, 4-way, and 6-way direction control valves that allows you to model your hydraulic system using the configuration that is already there or using a generic version. So before again going into the model, just some general simulation settings that we need to mind when we're modeling hydraulic systems. The first one is a solver setting. It is always recommended to use a stiff Rosenbrock solver when you're modeling hydraulic systems. I'll talk about where to change that when I open up the MapleSim instance. The second one is the fluid property. So that's a fluid property block that's present inside the hydraulic library. We recommend to have that always dragged in and put in the canvas, which will define the hydraulic fluid properties for the system that you're modeling. And the main characteristics or the parameters are the density, the bulk modulus, and the viscosity for the model that will be that you can add for the fluid inside the fluid block. All right. So let's get going. Start the first section for today, which is an introduction to basic hydraulics modeling. So I'm going to spend a little bit of time on the first section because we're going to talk about the basis of system level modeling in MapleSim, what's the concept behind it, how you can build models from a simple structure, and how you can develop or add complexity to them. And of course, these are all simple basic examples, but the idea is for you to apply it in your own modeling environment or in your own modeling system. All right, I'm gonna open up the MapleSim instance. I hope you have it open already. So what you see in front of you is exactly how MapleSim looks like. The center area is the canvas where you actually build the system models. On the left is where we have the built-in library components. MapleSim is a multi-domain simulation software, which means you're not just limited to mechanical or hydraulic systems. You have different domain systems that can be added into the system or into the model to build up the complexity or to actually get a full perspective of the entire model that you're building. Now, just quickly, briefly going over the library components, we have signal blocks under which you have different categories. So these signal blocks allow you to build some simple signals, mathematical functions, interpolation tables, relationships that you would like. And to build a model, you just bring and select the component that you would want and drag and drop it in the canvas to build a model. It is a drag and drop environment. You can just simply build that by dragging it into the canvas. I'm gonna delete that component for now. We have electrical library. We have 1D mechanical, categorized between rotation and translational components. We have multi-body, which incorporates 3D multi-body dynamics into the system that you're building. We, of course, have hydraulics. I'm not going to go into each and every session. We've seen it in the presentation, but we'll do them as we start building the models. Now, when I spoke about the simulation setting, that's on the right side, which has the simulation setting for the environment that you've opened up. The first setting allows you to define the solver. Like I mentioned, for hydraulic systems, it is always recommended to use Rosenbrock. So I would suggest you click on the solver and select Rosenbrock so that that is the solver that is set for this instance of MapleSim. Now, the other setting is multi-body setting, which we're not going to look into much. I'm just going to leave everything to default, and I'm going to go back to the canvas. So the first model that we're going to build for today is just a simple flow through a pipe model. To do that, I'm going to first drag in the components, and then I'm going to explain what I'm doing as I do them. So under the reference block, I'm going to drag in the tank. And as I mentioned, you need to drag in the fluid properties to define the fluid property of this model. So when I click on each of those components, you can see the parameter pane that highlights on the right. This parameters allows you to put in the values of the parameters defined for that component. In this case, I can define the fluid density. And for hydraulic modeling, the hydraulic fluid is assumed to be incompressible. So you define the density is going to be constant throughout the simulation interface. So you provide the density, you provide the bulk modulus, you provide the fluid viscosity. And the global setting includes the atmospheric pressure and the area min, which is used for the minimum area, allowable area for different orifices and valves that you can specify here as well. So these are all common parameters that reflect the entire system in this instance. So let's go ahead and build the first model for today, which is flow through a circular pipe. So I've dragged in a tank component. I'm going to go into the restrictions and I'm going to bring in a circular pipe. Now this circular pipe component models the Bernoulli's equation that defines the pressure and the flow rate. It also has frictional losses, which accounts for a pressure drop inside this component, which is included in. I will talk a little bit about the equations inside this component soon, but let's just finish the circuit by going further down and bringing in a source component to basically model a source for this circuit. I'm going to drag in a signal pressure, and that's what I'm going to give a signal pressure source to this model. And of course, I'm going to drag in another tank to complete the model. So I have almost all the pieces together. I'm going to just spending a little bit more time on this model because this is the basic model, allows you to show how you can start building from ground up. I'm going to zoom in a little bit. And what I'm going to do is connect these components together. I can do that by highlighting the ports and connecting them to form the connection. I'm going to connect the pipe. I'm going to connect the other end of the pipe to the tank. And in this signal pressure, basically what happens is whatever signal that I provide inside will provide the pressure drop across this component. I'm going to hit reverse so that I have a positive pressure drop in this direction. So I have all the components that we need. Clicking on the circular pipe, just exploring a little bit on the parameters for the circular pipe. You can define the length of the pipe. You can define the inner surface roughness. So like I'd mentioned, the circular pipe incorporates friction losses to take place in the model. So there are two types of friction losses that we account for. One is when the flow is laminar, and the other one is when the flow is turbulent flow. You define the surface roughness inside and the friction losses accounting for the surface changes. Now we have two different parameters here, which is the Reynolds number transition from laminar to turbulent. You can define when the transition happens in your model. And we also have an inner diameter defined in the system. Now the final value that I'm going to add is a step component to provide a pressure source to this model. I'm just going to connect the step here. So this will be the pressure. The step will define the pressure that I'm providing to this model. I'm going to say that for 2 seconds, it's going to be 0. It's just for demonstration. And I'm going to add, after 2 seconds, it's going to increase to 1 to the power of 4 pascals. You can define the unit of the pressure that you are determining in this input by clicking on this pressure block and changing the unit that you would like. For now, I'm going to leave it to pascals. So here it is. We have a model built. So essentially what happens is when you're trying to build a model from ground up, we have defined all the components in the library. You bring that components in the canvas. Each of those components have a certain set of equations that define the dynamics of that particular component. And let's say that is the dynamics that you want to simulate. You drag the component. We take care of the equations for you. MapleSim does that. So you drag in the components, make the connection. And when simulating the result, what MapleSim does is it assembles a set of equations to form a system of equation, solve that equation, and give you the results as a function of time. Now, in order for me to get the results as a function of time, you can directly do that in the result manager window once I simulate this model, or you can add probes to the system. For now, I'm going to right click on the circular pipe and I'm going to click on attach probe option that allows me to probe the variables that I want to see in the result manager window. In here, I'm going to measure the pressure, the volume flow rate, and I'm also going to measure the Reynolds number just to see what kind of flow is happening inside this model. And I'm going to hit generate. So like I said, once I hit generate, MapleSim will assemble the equations in, compiles, solves the equation, and prints the results in the result manager window, which automatically opens up. I'm going to just expand the results here. I'm going to press this to fit the screen within the system, and you can see the flow rate that I'm measuring, the Reynolds number that I'm measuring, and also the pressure drop, which I've provided in the system, which is 0 for 2 seconds, and then it increases to 1 to the power of 4 pascals. So now what we're going to do is I'm going to save this model as original, and I'm going to keep adding few complexity to the model and see what will be the changes to the system because of that added component. For example, let's say that I'm going to add an inertial element into the model. I can do that by going into the hydraulics library. Under the restrictions, I have a fluid inertia component. So this models the inertia of the fluid that is involved in this system. So I am going to bring that in. I do that by just selecting it and putting it in between the connection points, which will automatically make the connection. If not, you can just delete the connections and connect the ports with respect to one another to get the results. For now, I'm going to leave everything to default. I'm not going to change any values here, and I'm going to hit generate. And what this does, it will overlap the old results that I've saved with the new results for the ports that have the same name. Now, because I haven't changed the name of the ports here, it's just going to overlap results on top of each other and see what are the changes when I've added, that has happened to this model when I've added this fluid inertia. So looking into the model, you can see that, of course, that's expected. I can click on the zoom in to zoom in the model. I'm going to link all the plots together by selecting this. So when I zoom into one section, everything else will be zoomed into. And this is the expected results that we see. We see a system that is providing a lag in the model because of that fluid inertia. So now what we're going to do is I'm going to open up the presentation and kind of talk about what's the equations associated to the model and what's happening in the background for the first model that I showed. So let me open up the presentation. And there you go. So this is the first model without the inertia. A simple model. I have a pressure drop. I have a circular pipe and tank. And we saw the flow rate that is happening. So what's essentially happening in the right is I've just solved the model analytically for one instance of time and just printing out the results and comparing if the results match the actual value. Now here, like I'd mentioned, we've just used the Bernoulli's equation inside the flow through the pipe. So this is the relationship for the pressure drop as a function of velocity by applying the Darcy's friction factor here. Because we've assumed laminar flow and the Reynolds number is, I think, around 200, and that is a laminar flow. The friction coefficient is given by the equation that I've defined. These are all general equations that we can find online that we would have studied in our first year of engineering. Now, what I'm doing in the next step is substituting the known quantities at time t equals 2 seconds. If you would have noticed, at t equals 2 seconds, that's when I'm increasing the pressure from 0 to 1 e to the power of 4. So these are all the known values that I have because I know the density from the fluid properties, I know the pressure drop that I'm giving in the model, I know the diameter, and I know the length of the pipe. I substitute all of this back into the first equation and solve for velocity. Once I have the velocity, I'm using V in the flow rate equation. That's the simple relationship between velocity and the flow rate to calculate the flow rate, which in this case was 3.2 e to the power of minus 5, which is exactly what you see here at time t equals to 2 seconds. So I kind of wanted to show this very basic model to give you an idea of what's happening in the background when you're solving such a simulation in MapleSim. This is easier when you're doing a simple case, but what if you're adding much more complexity to the model? Building hydraulic systems with a lot of complexity in, it's going to be hard when you do it by hand, doing each and every calculation, figuring out when the valve opens, all the configurations that is required to actually solve this by hand. And that's what we do. MapleSim takes care of all the equations defined in the model, and you just connect the components, define the fidelity and the right parameters that needs to be put into the model, or the right dynamics that you want to capture in the system, and then you simulate the results. And that's exactly what MapleSim does it for you. Now let me go back to the simulation, and we're going to talk about the next model, which is, let me open up section under section 1. So let's go back to this is the workshop download file that I had sent. Under section 1, we have the third model, which is controlling a flow path example. I'm going to click OK. That opens up this MapleSim model. Let me simulate the results, and then I'll talk about the model in detail. So this is an example where I'm trying to control a flow path by providing the 2 lines here and determining how I can control it by making use of a spool valve. Now here, the left side is very similar to what you would have seen in the previous example. I have a tank, I have a flow rate, fixed flow rate that I'm providing into the model. I have a fluid inertia, and I have a circular pipe here that is connected to 2 pathways. One pathway is a spool valve 1. Now this is a spool valve that opens up or closes based on the input, or restricts the flow based on the input that I provide, because this input is directly proportional to the area of opening or closing in the restriction. So what I'm doing is I'm defining the area by means of two ramp function. I'm saying that, okay, this ramp will be open for 5 seconds for this particular area, and then I'm going to reduce it to 0. And the same case in the bottom, I'm doing the vice versa. It's going to be closed for the first 5 seconds, and it's going to open up after as a ramp function of 2 seconds for 1 e to the power of -5. Now I have two circular pipes for the flow, and all I'm doing is I'm probing the flow rate on path 1 and path 2. Now, like I mentioned, to probe the models, you can either right-click and say attach probe, which will attach the probe for this component alone. So it will measure the whichever variables that you're doing that you want to visualize across the component. Or you can select the probe plot option here. Like click on attach probe and select it anywhere in the circuit that you would like or anywhere in the ports that will measure the flow rate for you. So because we've simulated the model, let's see the results on top of each other. And now you can see the flow rate, the volumetric flow rate of both the paths. I can overlay the results on top of each other by just selecting this and dragging it and dropping it in the system. And now that way you can compare two plots in this very same instance on top of each other just to see the comparison of what works and what not. And this makes sense. I'm just simply measuring the flow rate for this model, and that's what you get. So let's move on to the next model for today, which is the fourth model, I believe, the water hammer model that we have here. I'm going to open it up, which opens up the model. I'll just press Ctrl-T so that you can have everything within the range of the system, within the range of this canvas here. So let us go over what's happening inside. So we've seen simple basic examples, and now this is a model that solves the concept of water hammer modeling. Water hammer effect is nothing but when a valve suddenly stops or restricts a flow in a pipe, what happens is a pressure surge, which is due to the momentum change in the fluid inertia. The pressure surge basically bounces off the closed valve and travels up and down. So before explaining, let me simulate the models to save some time, and I'll explain what's happening in the model. So here on the left, we have the components that we're familiar with from the previous examples that we've seen. So that is a tank, we have a fixed pressure source, we have a circular pipe, and we also have an inertia model that you see here. Let me close this window so that we can open up the model. Now what I've done is we have followed a lumped parameter approach to discretize my pipe into 20 different sections. So that's what you see here. This is a pipe that has been discretized into 20 equal sections. And how I've defined it is, first, I've defined the parameters, the top level parameters of this model by using this parameter block. This parameter block can be created by clicking on add a parameter block, which allows you to define the top level parameters of your entire system. And this becomes quite useful when you're dealing with huge models that has a lot of subsystems to go in. You define all the parameters that is required on the top level here, so it's easier to change the values one after the other. So I've defined the parameter block. I've defined that I've discretized the number of sections of the pipe to 20, and I've defined the properties of the pipe, the properties of the subsystem inside. So let me quickly go over the first subsystem. They are all shared subsystem, which means whatever changes I make to the first section will be reflected in all other. And again, this becomes useful when you're dealing with systems that share common subsystems. So in here, I'm modeling the pipe, and I'm adding a little bit of fidelity to this model by adding the circular pipe, adding a fluid inertia for the pipe, a flow resistance will be added in. Pipe compliance has been added by making sure I'm using a compliance cylinder here, and all of the values are parameterized. So the values will be acquired from the top level system that we have. On the top here that you see is nothing but just simple visualization aids that we've created. Hydraulics is a 1D modeling environment without multi-body or 3D modeling. It is just plots and graphs. So in order for us to actually kind of visualize what's the flow rate or what's the pressure surge that's happening inside, what we've done is we've used a pressure sensor to measure the pressure, and then I've attached it to a prescribed translation for this cylinder. So this cylinder will basically go up and down as the pressure surge happens, and I'm also using a color blend gradient to this cylinder so that you can change the changes in the color as the pressure increases. And that's common for all the subsystems that you see in here. Now on the bottom right, you have a spool valve, and this is the valve that restricts the flow after 2 seconds, which I'm providing by means of the signal. So after 2 seconds, you should see the pressure surge in the system. And if I open up the plots, you will be able to see that this is the transducer inlet that measures the pressure in bars. We have the pressure surge that's happening here in the probe and the flow rate after 2 seconds, which becomes 0. Just for fun, we've added visualization for the system as well. So when I simulate the model, you can actually see those multiple 20 cylinders just going up and down because of the pressure increase in the water hammer model. So we've seen, okay, from building a simple model from ground up to actually conceptually designing a concept in MapleSim. Now, let's say I want to attenuate this water hammer model, for example. How would I do that? You can make use of different components that are available in the library to do that, or you can create your own custom component. For now, let us open up, just to save time, I'm going to open up the water hammer accumulator model here. And all this did is I've attached an I'm just pressing Control D for zooming in, and just attached an accumulator model. It's a spring-loaded accumulator from the library components. And if I look at the accumulator, we have accumulator section. We have 2 different accumulators. I've gathered the spring-loaded accumulator here. Just going over what this component is. This is an accumulator with a spring-loaded back pressure. So what happens is, consists of a preloaded spring that is measured at a certain pressure. That's the pressure preload that you've defined here. And inside the accumulator is a piston hydraulic chamber that is connected to the port. Now, what happens is when the fluid pressure at the port exceeds the preloaded pressure that I've defined here, the chamber will move the piston, compressing the spring inside, and that's what's happening. You can define the geometry of the accumulator here based on how you would like and how much you would want to accumulate or store the energy. I'll just simulate the model and talk about it a little further. So that's what I've done. I've just gathered a spring-loaded accumulator, connected it into the component, and I'm going to simulate the results and see what will be the effect of this accumulator. Is it able to attenuate my model, or do I have to change the parameters in? What can I do? And that's what I'm doing here. Now, the simulation resulted for 3 seconds, and you would notice that I've already saved a model without the accumulator. So that's the one. You can just remove it, or you can select this and press Control E, which will suppress this model in the instance of the simulation. It's going to leave everything to default, but yes, you can. This is an overlap of the results that we see, and you can actually see how much the accumulator is able to attenuate the system response. So I just link all the plots, and you will be able to see the attenuation of the plots, mainly because of the accumulator and how much it has damped down the system here. Now, as a fun thing for the 3D playback, what we can do is we can overlap the results on top of each other to see how the system response is. For example, the previous model, let's quickly change the color of it to say that it's gray, and I simulate the model, so the 3D playback also overlays on top of each other, and you can see the gray is the highest, the previous model without the accumulator, versus the green, which is the new one. All right. So that ends the first part of the simulations of the webinar here. So let me go to the second section for today, which is working with, as the name indicates, it's working with valves and cylinders. We're going to talk about, very similarly, we're going to talk about bringing in different valves and cylinders and how we can model that using MapleSim. We're going to also use some multi-body components, meaning we're going to merge 2 different domains together and see how that would work with MapleSim. So for that, I would like you all to, let me close these off, open so that it's easier. All right, perfect. So let me open up the section 2 and a simple scissor lift model that you see here. The model 7 is the scissor lift model. This is just a purely mechanical model that I've attached in this, but we'll discuss about it soon. So let me quickly open up the scissor lift model. So this is a model that combines 2 or 3 different domains together. One is trans 1D mechanical domain. We're also including multi-body domain as well as hydraulic domain. So quickly going over the mechanical part of the system. So I know that scissor lift mechanism is kind of, as the name indicates, is a scissor lift gantry lifting mechanism that is modeled in MapleSim. Let me go inside the section and explore a bit deeply on what's happening inside. Inside the subsystem are 2 other subsystems. The first one is the lift, actually modeling the lift of the model. If I click on it, all you see here, I'm not going to go deep into what these components are, but essentially what I'm modeling here is by making use of the multi-body library that you see here, with bodies and frames, joints, and rigid bodies. I'm modeling the lift mechanism by making use of that. each of the subsystem associated to each of that lift or the frame that we've modeled. There's a point mass for each of the model, and the mass has been the mass is parameterized, and that's what I've done. I've provided the necessary degrees of freedom to make sure that my mechanical model works fine as expected. Once I have that in place, I am actuating the system using hydraulic model. So that's the mechanical part of the system. If I click on this hydraulic lamp, and what you see here inside is a translational spring damper model. All this does is that applies stiffness, damping, and actuation to the frames that it's connected to. One, it's connected to a mast, and the other one, it's connected to the mechanical system. So this is that actuator that actuates the model. And the actuation or the displacement that happens inside is provided by the hydraulic model that is outside of this section. And you can do that by seeing this port here. So this is the 1D mechanical port that is connected to this translational spring damper actuator to basically provide the displacement between these frames that would lift the scissor lift model. Going back into the system, again, clicking on home will give me the first model here. What I'm going to do is I'm going to hit generate so that we can see the results, and then I'm going to talk about what's happening in the hydraulic section. So like I said, we are actuating with the hydraulic components. So what I've done here is I first attached a hydraulic cylinder. This hydraulic cylinder will undergo an ideal transformation between hydraulic and 1D translational work. And that's what I've done. You have a hydraulic port here, for it's a single acting hydraulic cylinder, a hydraulic port here, which is connected to 1D translational port, which in turn is connected to that translational spring damper actuator to actually provide that forward motion for the model, or the motion according to how the valve is actuated. Now I've used a 3D DCV 332 selector valve, which you can find under hydraulics. If I go into the direction control valve section under 3-way, you can find a DCV 32 selector valve. So this is the valve based on the configuration that you provide, which is the input that you give to the system, which is here. And that's the input that will determine which configuration this valve needs to take and when. So that's what I've done. I've used the 3D 32 selector valve to actuate this scissor lift mechanism, and I'm providing just a very simple fixed pressure source of 250 bars into the model. That's all I've done. Provided a pressure source, connected it to a DCV valve, and then attached it to a hydraulic cylinder, which will move the piston and then actuate the scissor lift mechanism that we see here. Now the input is just nothing but a pulse that I've obtained from the signal block library, and I've also provided a simple first order lag for this model, just for showing the effects, and that's pretty much it. Based on the actuation, based on the spool displacement that I provide, the valve will shift between the two configurations that I've determined. I've already simulated the results, so let's open up and see what's happening. I'm going to click on the 3D playback here. You can arrange them as however you would like. And that's what I've done. I've clicked on the 3D playback to see what's happening in the 3D window and also the plots that you see on top. So when I simulate the results, you can see, okay, this is my gantry height that's going up and down, basically actuating this translational damper, which is provided by my hydraulic actuation. And of course, it's not specific to hydraulic. You can combine different domains together, electric actuation, different things that can be done. And that's the advantage of using MapleSim, because with this tool, you're combining different one or two domains, many domains together to understand how the interaction works within the tool itself. All right, so now let's open up. I'm going to close this model now. And let's open up the next model that we have for today. Let's close this too. And open up the next model, which is the regenerative circuit model. Again, this is another example that shows multi-domain modeling in MapleSim, but I've used a DCV, I've used a different type of DCVs to actuate the system. So let's quickly go over what's happening in the model, or what this two model consists of. So this is, as the name indicates, a regenerative circuit. And on the left is where we've implemented the concept of regenerative circuit here. And all this means is you are trying to save time for the extension, or trying to extend this cylinder much faster by just driving the B port of the cylinder or the hydraulic line back into the pump component of the DCV. So both the flows are acting in order to extend the cylinder much faster. Going over the components one by one, I have a fixed flow rate source that I provided to the model. There is a relief valve that I've obtained from the system. You can find the relief valve if you go down to the sections and click on the valves category. and you can find the relief valve here that you can drag and drop in the canvas. The relief valve is basically set as a valve that will protect during catastrophic failures in real systems. That just measure that the P open will open up at about 1000 psi, for example, how much ever the valve can, the system can take. This is connected to a DCV43 pump to tank model. I've obtained that by clicking on the DCV 4-way valve and just selecting the right configuration that you would want for this actuation. And that is connected to this linear actuator. This is a double acting hydraulic actuator that you see here. So 2 hydraulic ports and 1 mechanical port. Now you can define the areas of both the piston side, the cap side, and the rod side of the cylinder can be determined by defining the area. You can also add piston viscous friction coefficient if you'd like to add some sort of friction between the sliding piston, and then different other components or other parameters include an end cushion, which I've activated. Basically what this does is it will set the maximum length of my cylinder to the value that I've specified. And if it goes beyond it, there will be a contact which will provide an opposing force to stop the system to not go beyond that certain limit. And that is done by a simple spring. I've provided stiffness and damping, so it just uses the spring damping characteristics to define that. Now, that's the right-hand model that I have. The input to the DCV is using this ramp that just changes the configuration based on which configuration I want to take part in the system. On the right is just a comparison of a circuit without the regenerative circuit. So you don't have the B port that is directly relating to pump. It is just a simple model. I'm going to hit simulate, and I probed the displacement and the velocity on both sides of both of the circuits here, so that we can see a comparison one on top of other. So here we have the piston regenerative circuit. You can see that the extension stroke is much faster in comparison to the one with the original model. And I guess that's the idea of adding such a system. I know that there's a lot of hydraulic presses out there that uses this concept, but the idea here is for me to show you how you can utilize these different valves to build your model from ground up. We have a velocity comparison, which is as expected. You can see that the regenerative circuit starts with a higher velocity, and the same with the flow rate comparison. All right, so now this ends the section 2 for today's workshop. And now I'm going to open up the final section for today, which is what you're waiting for. It's the injection molding machine example. For that, I'm going to open up section 3, and I'm going to start with the first model, which is the injection molding machine. That's the 9th model that you see here. Let me close off the other ones. All right. So what the idea of this model here is to first start with a basic hydraulic circuit of that injection molding machine, and then building them and adding complexity as we go forward. So how do we do that? The first thing is, yes, you define the hydraulic, all the hydraulic components associated to your system, any system, not just injection molding machine, any other system that you have. You can do that by using the components that we have in the library, and that's exactly what I've done in the system. So let's just quickly go over the inputs provided, or just talk about the model in general. I have a parameter block that I've defined. This defines the parameters for this model here. The parameters are the diameter on the A and B side of the cylinder, which I've parameterized, that you can change according to how the values that you would like. Now the inputs that is going into the model is in the bottom. I have a speed input that is provided to the variable displacement pump that you see in the library. So that's the speed input that I've provided, and you would notice that this icon is a bit different than what you would have seen from the signal block library. So if I click on that, all it does is it opens up an application in MapleSim. So this is, I will talk a little bit about apps and templates very soon, but what I'm doing is I'm using this 1D motion generation app to create a custom motion that I would like. Let's say that your signal is particularly different from what you can see from the general signals from the signal block library. You can use this to create the signals, but the advantage of using this 1D motion generation app is it's not just an app created for signals alone. You can use ACOS supports, as in you can create translational, rotational angle, or rotational velocity as well using this app. And that's what you do. You can specify the time, you can specify the different shapes that you would like for different sections in this motion generation. You can define however the shape wants to change. Everything can be defined here based on the options available. Let me close this off. So that's what I've used here to model the speed, input speed for this model. And on the top, I've used a DCV43 floating valve from the DCV library palette. And the input that we see here is the spool actuation. I've used different ramps to change between the configurations inside the DCVs. I've used an add to add sum up basically all of these. Let me first simulate the model, and then I'll just go a little bit deeper into the components. Now, if we click on the DCVs, the configurations that you see, or the input that you see here, is the spool displacement, right? Like providing the spool actuation to the model, which will change the configurations. The configuration varies from -1 to 1. -1 being the leftmost configuration, and 1 being the right configuration, and 0 being the center configuration. So that's how you would define the input to the spool stroke that you want to provide for this model, and that will change the configuration accordingly. And this DCV is connected directly first to the double acting cylinder that you see here. I've also attached two valves. These are check valves, which are, I believe, used to remove or used to avoid negative pressure that happens, or back pressures that is happening within the system. And that's how I've set up here. And of course, these relief valves are also used to maintain a preset or a maximum pressure differential that the system can allow between the cylinder and this DCV. Again, this is a very basic mock example that we've taken. We've not taken any specific injection molding example that is available out there. This is just an example model that kind of shows you the options that you have available, or the different methodologies or different apps that you can use to improvise your own model when you're building in MapleSim. So we built the base model. What else can we do? Of course, not all dynamics you would be able to capture all the dynamics in the real system as opposed to simulation environment. You start to add the dynamics the fidelity one by one. As in, the one example would be to change your valve that you have here. It's just a linear translation between linear opening between the different configurations. You would essentially want to put your manufacturing data, the manufacturing data that is available for the valve that you use in your real system. You would want to do that. So in order for you to do that, we have an option called generic valves. So if I drag and drop this generic valve, that there are options that says characteristic curve. I'll just unselect the use case and select the characteristic curves that allows you to put the custom characteristic curve of the valve that you're using. Essentially, you would want to get the manufacturing data and put that directly in. So we're doing this is because why we're doing this is because, of course, whatever valves that we use or the systems that you are using to model this particular system in MapleSim, the more fidelity and more accuracy that you are replicating compared to the real system, the more accurate your results will be. And that's what we're trying to do. We're trying to improvise the system to make sure that every other valve is similar to what would have been in a real system, and see how the response will affect the system, affect the model. So in here, you can see that there's an option called inline, where you can actually put the spool opening stroke as a function from -1 to 1 as a function of the area, or you can define Excel worksheets. For now, I'm going to select the attachment, which allows you to attach the Excel file. I already have a valve characteristic _A that is defined that I've attached in as part of this session I'm going to select that. If you have another Excel file that you would like to add, you can click on New Attachment and browse through your file explorer to select that particular Excel sheet. I'm going to leave this to valve characteristic, and I'm going to show you where I've attached the model. Under the attached files, under the valve characteristic _A is where I have the Excel file. When I open it up, you can actually see what's happening here. So left is the input spool actuation, or the spool displacement, or the stroke, if you would call it, that varies from -1 to 1. And these are all the areas for the various paths inside the DCVs. The order should remain the same. The order is mentioned on the right here. We start with PA, which is a spool from portion P to A. We take PB, TA, TB, AB, and PT, and you define the area of opening for all of them. This is just an Excel plot that kind of shows you how the openings are for the valve. I'm going to go back into the model, and I'm going to kind of open up, add the two volumes to provide volumes to the fluid line here, and I can delete the system. Before I delete, let me show you the results, what it is right now. And what I've measured here is the cap side and the rod side pressures. I have my DCV command that ranges from 0 to 1 to -1, and I have a piston displacement, and I also have the piston velocity. Now what I'm going to do is I'm going to delete this component, and I'm going to add back the new component that I've developed, which has the new characteristic cav in it. So this becomes in this way, my model is one step closer to replicating the system exactly like how a real system would work. And now, of course, there are a lot of things that you can add one by one once you know a lot about your model and see which are the dynamics that you want to capture in the simulation environment. For example, let's say I want to add a friction for the sliding, a stripe friction, for example, for this piston mass that is sliding. I can do that by adding a friction component. I'm just using a shortcut to select the friction component here. But essentially, this is available under 1D mechanical library under translational. Under translation, we will find the same thing, which will apply a translational a friction between the sliding masses that you have connected it to. Now I'm going to add a fixed frame on the other end. I can just copy this because I have it here, and I can paste it on the other end. And I can make the connection respectively, and now I have a friction. Clicking on it, you can define what are the different frictions that are applied because of this. There's a sliding friction force. We have Coulomb's friction force that can be added as a viscous friction coefficient, very similar to what you would see inside the cylinder. We have Strybeck sliding velocity. So these are all different types of frictions that are incorporated in the model that you'll be able to make use of. I'm going to jump a little bit because I want to save some time and open up the second model, which has a setup based on what we're going to do for the next steps. So let me open up the next model that we have, which is the 10th model, injection molding machine controller. Let me open it up. And well, there's not a lot of difference from the previous model, except I've added few small increments to this system. One increment is if I open up the subsystem block here, it's the same component. Everything is the same that you see here. I've added the friction and I've measured the force and the velocity profile for this friction component. But what's added is this motion generation, 1D motion generation app. I've created another signal that would give me the set displacement that I want my controller to follow. Essentially, this is a model where I'm trying to tune the controller to make sure that it resembles the actual system. So let me simulate the results so that we can see that and go over the system here. On the right, I have two sensors, the position and the speed sensor that I'm measuring. On the top level, I have a simple PID controller. So this is it's a PID controller with a limited output, because what it means is the proportional gain is coupled with the integral and the derivative gain inside the component. I have parameterized the gains for this controller inside this parameter block. So the areas of the cylinders, the added mass or the mass of the moving platen is defined, and also the gains of the cylinder is given. And when we look at the results, you can see, well, the controller is doing its job, but not a great job. You can see that the set and the plant positions are kind of off by a lot, maybe by a bit. And the idea here is to try to see how you can control or how you can tune this model. You could do that by running multiple simulations, playing with these values and defining it, or you can use the apps and templates section. In this apps and templates section, you have multiple applications that are built in as part of MapleSim that allows you to create allows you to analyze your model efficiently. Now, one app that we've already seen is the 1D motion generation app that I showed before. The other app that I'm going to talk about is the parameter sweep app. The idea of this particular analysis is I want to use a parameter sweep app. Let me double click on it. I want to use this app to tune my controller. I know that I've parameterized the system. I'm going to hit load to load the model here. And once the loading is complete, what I'm going to do is I'm going to display all the parameters I have, and I'm going to sweep through the parameters for a set of data points, simulate the results, and see which will be the most appropriate value. For example, I have my K, or the parameters will list, or once I've loaded the model, what happens is this app will load the MapleSim model and display all the parameters defined in the system. And I'm going to add the K. And I'm going to say, okay, I want my K to maybe vary from 0.1 to 0.5. Right now it's 0.1. Let me vary from 0.1 to 0.5 for 3 data points. I'm going to add my TI, which is the integral gain, for example, and I'm going to change it from 0.4 to 1. Right now it's 0.5. Let me change that, and I'll add 6 data points. And then I'm going to add the derivative gain. Integral gain, I haven't added it, so I've added 0.4 to 0.6 for 6 data points, and I'm going to add derivative gain in here, and I'm going to change the configuration from maybe 0.01 to 0.6 for 6 data points, and then I have all these three. Let's click on the outputs and see what are the outputs that can be helped to simulate the model. These are all the output probes that we have. I'm going to measure the plant position, for example. I'm going to measure the pressure ranges. This is the PA and PB, both sides of the cylinder that I need. And I'm going to hit run parameter sweep. Once I hit this parameter sweep, what happens here is this model will compile and then simulate the results by sweeping through the different simulation data points that I provided. I think I provided around 100 different combinations, and that's what it's doing. It's running 100 different simulations to figure out what the envelope of the system results would be. How would you, how can you build, which parameter can be chosen for this particular model. And this becomes quite easier in comparison to what you would do in an actual, what you would do by just running multiple simulations, one on top of other to see what happens. All right, perfect. So now what we see here is a profile or the envelope of the different parameters that this model has swept through to find out what will be the profile for the different configurations or the possible combinations of the three parameters that I've chosen. Now you can unselect this plot envelope here. That will give you what will be the values. There you go. That will be the overlap of about 100 results on top of each other. And of course, you can try to modify them by fixing one value at a time and figuring out, okay, maybe I'll change my gain, for example, to a certain value. In this case, let me make it 0.4. Let me change my TI here and figure out which will be the right value that I need to change so that I get my system response quite accurate to the actual system. And then if I go on TD and I fix the model and see which value will be much better. And you can see that with 0.001, I see a nice profile that I would like for this model. And that's what I do. I define my TI, TD, and K, and I go back to the model and put it on top of each other. Just to save time, I've opened up the new simulation because I've lost the connection. Let me drag and drop the new simulation instance here. I apologize for that. So here what I've done is, based on the parameter sweep results, I have implemented the K, TI, and TD gains for my parameter block. And this is the idea. You have a problem, you want to solve that. You have different parameters that you want to tune in and see what that changes, what will that change reflect on the model. And that's what I've done, making different changes using the parameter sweep app to sweep through the parameters and give the results, display the results on top of each other to see which will be the most appropriate response. If I click on this model, the other thing that I've included as part of the system is the CAD geometry. MapleSim has the ability to open up, to bring in CAD geometries into the model and simulate the results. And that's what I'm going to do. I'm going to show you just briefly on how you would do it. I'm not going to go in deep of what's happening here. Essentially, what you would do is, if you have a CAD geometry in play, you can select that by going on to File, Import CAD. MapleSim supports a lot of varieties of CAD extensions that you can do, from SolidWorks to CATIA, which you would want to open up and generate. I'm going to, for now, go into the attachment and open up the entire assembly to kind of show you what's happening once you import the CAD. So once I import the CAD toolbox will open up, and this CAD toolbox allows the user to look at the model, figure out what are the multi-body frames that needs to be added. So by adding these frames, what happens is you separate the components, you add the frames, and these frames allow you to apply motion, are connected to other components in the library by making use of adding these coordinates. And that's what I've done here. You can see there's just two main sub-assemblies that I want for this model. One is the base, which is this entire model here, and the other one is the moving platen, because we are seeing the translation of the moving platen, and that's what I've done. I've created that, and I've added ports that you would, the coordinates or ports that you would want to see. So in this case, the ports that you see here can be done by making use of adding coordinates on the top. So this is the option that you have. You can place the coordinates, and that will allow you to add the multi-body frames that you would like, where you can connect this component to other components in MapleSim to apply motion to the model. Now I'm going to go deep into this, and I'm going to come back, and that's what I've done. I've attached these two components here that you see with ports that you created using the coordinate ports. And what I've done is I've added components from the multi-body library to apply motion. In this case, this is my hydraulic circuit I have, and this translation is directly coupled to this prismatic joint, which you can find from multi-body under the prismatic joint, under the joints in motion here, which is what I've done. And I've connected it to between the moving platen and the base, because it's translating with respect to the x-axis of these two components here, and I've just fixed the model on one end. Now, if I look at the simulation, so this is a simulation with the controller that is being tuned, as well as the CAD that has been added, and the simulation results are here. This is the overlap of the set position versus the planned position, and you can see that the controller is doing a lot better job. And now the playback window that we have that will incorporate the CAD, where we have incorporated the CAD in. I'm just going to simulate the results so you can see the actuation of the moving platen or translation of the moving platen with respect to the base frame. So idea is bringing in a CAD geometry not just is used for visualization, but it actually brings in the mass or the inertial properties. Well, in this case, because it's just translating, it's a single axis model, it brings in the mass properties of the model from the CAD geometry itself. And that's the advantage of using the CAD model here. Now, this is one type. Again, it's just a mock example that I'm showing you, but the idea is once you started with a base model, you add more complexity into the system, and then you try to figure out which would be the better design for your model. And another example that I have, other than the apps and templates that you see here, is an attachment. I hope you please open that up in your free time, just to look at what within few commands or within click of few commands, you'll be able to create your custom, you'll create a custom application that allows you to change parameter values or change parameter values and see the results, how they reflect in the system. And this is again another tool that MapleSim has, which is Maple, and Maple is the mathematical engine behind this system, which allows you to perform customizations for the model that you have in the system. I strongly encourage you to open this up in your free time and look at the apps. Because we're running short of time, I'm just going to go ahead and talk a little bit overview of a few other things that I want to point out. One thing is under help, under examples, under physical domains, we have different example models for different libraries. I encourage you to open them in your free time to look at the examples and run them. And the other thing is under the apps and templates, apart from the parameter sweep app that I've shown, there are multiple apps that you can use to perform analysis. Optimization is one example. The other one, I think a lot of customers who are involved in automation industry would use is to test their controller logic against this plant model. So once you have your plant model set up, ready to go with all the components and nuances that you wanted to design, what you can do is you can import this model, this plant model, as an FMU, which is a functional mockup unit. You convert this model as an FMU, and then you can put it in any automation tool out there, which will be able to import the FMU and test your controller logic against this virtual plant model. And that's what we call as virtual commissioning. All right, so this ends the presentation for today.